We're doing section 14-2 in this video, and our objectives here are to use ray diagrams to find the position of an image produced by a converging or diverging lens and identify the image is real or virtual. All right, very similar to what we did with mirrors. Solve problems using the thin lens equation. We'll go through that, and you'll see that's exactly the same as it was with mirrors. Calculate the magnification of lenses, just the way we do with mirrors. And describe the positioning of lenses in compound microscopes and refracting telescopes. Okay, so let's get started. First of all, there are different types of thin lenses. One of the big differences between a lens and a mirror is that the lens is transparent and it allows light rays to go through. It refracts the light as the ray goes through it. And so the virtual and the real side of the mirrors are just the opposite that they are from mirrors. With a mirror, the virtual side is behind the mirror because light can't go through a mirror. With the lens, light does go through, and so the real side is on the opposite side of the mirror from the object. The virtual side is on the same side. If a lens is thicker in the middle than it is at the rim, that is a converging lens, and we'll see why that's called converging in just a minute. If it's thinner in the middle than it is at the outside, then it's a diverging lens.
A lens that is thicker at the middle than at the ends is a converging lens. Parallel light rays arriving at the lens are bent when traveling through the lens. All the light rays converge or focus on a single point. The point at which these parallel rays converge is called the focal point. It is to the right of the lens if the light source is to the left of the lens. A lens that is thinner at the middle than it is at the ends is a diverging lens. This lens behaves like the opposite of the converging lens. Although the light rays came from very far away, the lens makes them seem like they all came from a point closer to the lens. The focal point of this lens is to the left of the lens. It is where the light rays look like they originated, even though they actually came from very far away. The way the rays behave after leaving the lens gives them their names: converging and diverging lenses.
Okay, now just a couple of things there. First of all, she said that the lens is, she talked about the converging lens being thicker in the middle than it is near the ends. That's really the edges. Most lenses are round, or at least somewhat round in shape. If you think about glasses lenses, those are somewhat circular in shape. And so she should have said not the ends, because it's not a two-dimensional thing like this, but it's usually round. And this thin part here would go all the way around the outside. The thick part, of course, would be throughout the inside. And the same thing with the converging lens. It's thinner in the middle than it is near the edges. Okay, the focal point is where the image of an object at an infinite distance is formed. Okay, in other words, rays of light that are parallel to the principal axis will be focused at the focus if they are parallel, and if the distance is infinite, then the light rays are arriving at the lens parallel. What that means is that lenses actually have a focal point on each side of the lens. It doesn't matter which side you send the light through, the lens is going to do the same thing to parallel rays coming from the left or coming from the right. And so you could talk about the focus on both sides of the lens. And just like it was for a mirror, the focal length and twice the focal length. Now again, that's not necessarily the center of curvature for the lens, because different types of lenses made out of different materials will have different different curvatures to them. But at the points F and 2F are important in terms of where images, the location of the image or the object in the location of the image. And as with the mirror, the distance from the focal point to the center of the lens is called the focal length. What this means is when we're actually drawing diagrams with the lens, it's not real important that you have the lens, a real tall or a real big lens. It's important that you know where the center of the lens is, because that's where, in effect, everything happens. Rays of light are bent. We consider them to be bent only at the center. In actual fact, they are refracted a little bit as they enter and a little bit as they leave the lens. But we can, for all practical purposes, consider that all to be occurring on at the very center of the lens. You see that here. Here is the center of the lens, all right? And this ray of light coming in is refracted down to the focus. These are rays of light that are parallel to the principal axis, which would be right along here. And so these rays of light are refracted to pass through the focus. If we were to have parallel rays of light coming from the other side with the same lens, they will be refracted to a point here. So you actually have a focus on either side of the lens depending on where your rays of light are coming from. Our standard way of doing this is to place the object, or in this case the parallel rays of light, on the left-hand side, coming from the left, and so the focus and the focal length would be over here to the right. However, this one here, this focal length, is the same as this focal length for the same lens. And you see for a diverging lens, it's very similar. Rays of light parallel to the axis are refracted as though they were coming from this, as though they were originating from this focus right here. Again, because this focal length is on the same side of the lens as the object, this would be a negative focal length. This focal length here would be positive. This focal length would be negative.
The focal point of a converging lens is the spot where the image of an object at an infinite distance from the lens is focused. A group of rays parallel to the principal axis pass through a focal point F after being bent inward by the lens. The distance from the focal point to the center of the lens is called the focal length, F. For a converging lens, the focal length is positive and the focal point is to the right of the lens if the object is to the left. A diverging lens causes parallel rays to diverge. The focal point is defined as the point from which the diverging rays appear to originate. The focal length is defined as the distance from the center of the lens to the focal point. For a diverging lens, the focal length is negative to indicate that the rays appear to originate on the same side of the lens as the object. Both converging and diverging lenses have two focal points but only one focal length. However, since the convention when drawing ray diagrams is to place the object to the left of the lens, we do not generally speak of two focal points.
Okay, again with the lenses we can use ray diagrams as we did for mirrors to identify the location, or to help us find the location and the height of an image and the exact type of an image that is formed. The rules for drawing these rays are very similar to what they were for mirrors. For example, you have rays parallel to the axis. That is going to be parallel to the principal axis as it comes from the object to the lens. As it passes through the lens, it's refracted so that it passes through the focus. All right, so this will go through the focal point, F. And that's for a converging lens. We'll deal with diverging lenses in a moment. The central ray, this is the ray that passes through the center of the lens. Okay, that's right at the very middle. and that one just goes straight through. It's not refracted at all. Okay, so a ray of light through the center of the lens, that's where the plane of the lens crosses the principal axis. That will pass through straight through without being refracted. Then the focal ray is the ray through the focal point, and that gets refracted parallel to the principal axis. All right. Again, these same three rays on a diverging lens, the ray parallel to the axis will be directed away from the focal point, as though it were coming from the focus on the back side of the lens, on the same side of the lens as the object. The ray of light that passes through the center of the lens, again, is not affected. It passes straight through. And the ray of light that passes through the focus will be refracted so that it is going parallel to the axis. All right, what can you get? With a converging lens, you can get either a real or a virtual image. In other words, the image, if it's real, it will be formed on the side of the lens away from the object. If it's virtual, that image is formed on the same side of the lens as the object. The image produced by a converging lens is real and inverted when the object is outside of the focal point. In other words, if the object is beyond the focal point, the image is going to be real and upside down. When the image is at or inside the focal point, the image formed will be virtual and upright, and that is the way a magnifying glass works. We'll take a look at that in class.
When an object is moved relative to the focal point of a converging lens, its image changes. If the object is infinitely far away, the image will be an infinitely small point image at the focal point F. If the object is at a position outside of 2F, a real image will appear between F and 2F, smaller than the object. If the object is at position 2F, the image will be a real image at 2F. The image will be the same size as the object. If the object is at a position inside 2F but outside F, the image will be a magnified real image outside 2F. When the object is precisely at the focal point, the rays do not converge at all. If the object is inside F, a real image will not form. Instead, a virtual image appears. The light rays seem to have come from a larger image that is further away from the lens than it actually is.
Okay, so this is the situation that you have using a magnifying glass. You get the object close to the lens, and it magnifies it. It makes it look like it's bigger, but it also appears to be further from the lens than it really is. This object appears to be back here and appears to be much larger. Diverging lenses can only produce virtual images from real objects. Okay, the image is always virtual and smaller. That's the only image that you can get from a diverging lens, and you'll see that here.
A diverging lens can produce only one kind of image, a virtual image. To locate the image, start with a ray parallel to the principal axis. Since we know this is a diverging lens, it is easy to remember that this ray is bent outwards as though it originated at the focal point on the left. Draw a second ray that passes straight through the center of the lens. The image appears where the two rays appear to have originated.
Okay, and let me just point out, here is that ray of light that goes right through the optical center of the lens. This is where the principal axis and the plane of the lens intersect. A line drawn through that point goes straight through unaffected. All right, so this line looks like it's coming from back here. This ray appears to be coming from back down this way, and you get where those two intersect, you get the object here. So you have to, again, you have to use, as with mirrors, you have to use the rays as they're going away from the lens. In the mirror, we use the reflected rays. Here, we're going to use the refracted rays and follow those back. Where they intersect, that's where the object is, or the image rather. Okay, for thin lenses, you have to make the assumption that the lens is very thin. Okay, you can use this. We use this lens for all equations involving lenses, but technically it's not good when you have lenses that are very thick. Okay, and just as we saw before, 1 over the object distance, I prefer to use DO here and DI, but you'll notice this is the exact same equation we had for mirror. 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. Exact same equation. The magnification of a lens depends on the object and the image distances, and that's given in this equation. And again, I prefer to use HI here for image and HO for object. The magnification is the image height over the object height, which is equal to minus the distance, the image distance over the object distance. Okay, so again, this is exactly the same as it was for mirrors, and it's used exactly the same way as the one we had for mirrors. Okay, you can use the magnification to describe the image's size and location. And this chart, which is in your book on, let me see, it's on page 493. Okay. P will be positive when it's in front of the lens. It will be negative for an object that's in back of the lens. Okay, so depending on which side of the lens the object is on, P is positive or negative. Q will be positive if you have a virtual image, negative for a virtual image in back of the lens, negative if the virtual image is in front of the lens. And then F is positive for a converging lens and negative for a diverging lens. Okay, so this one is a little bit different because the converging lens, the focus is on the opposite side of the lens from the object, but that's the positive side. The negative side is when it's on the same side. The focus is on the same side of the lens as the object. Okay, let's work a sample problem. An object is placed 30 centimeters in front of a converging lens and then 12.5 centimeters in front of a diverging lens. Both lenses have a focal length of 10 centimeters. For both cases, find the image distance and the magnification. Describe the images. We'll move to this workspace so that we have some place to work. And I've copied the problem here so you can see that. Let's work with the converging lens first. Our lens equation, 1 over F is equal to 1 over DO plus 1 over DI, which is equivalent then to, if we solve this for DI, 1 over DI is equal to 1 over F minus 1 over DO. And we're given in the problem the focal length is 10.0 centimeters, and the object distance is 30.0 centimeters. So we can plug those values in here, and we get 1 over 10.0 centimeters minus 1 over 30.0 centimeters. So here's our calculator. So we have 10. I'm not going to bother putting in the 0.0 for the calculator. It's just the same. Minus 1 over 30 is 0.0666 and so on. And then we're going to take that to the minus 1, and we get our object distance of 15 centimeters. So we get DI equals 15.0 centimeters. All right, the magnification then is equal to the minus d sub I over d sub O. Now di was positive, meaning it's on the right-hand side of the mirror, so that's a positive number. So our magnification, when we plug our values in here, di is 15.0 centimeters. DO is 30.0 centimeters, and I can even do that one without my calculator. I get 0.500. No units on that. We're dividing centimeters by centimeters, so our magnification is 0.5. Okay, this will be half as big as the object, the image would be. Okay, and oops, I forgot my minus sign here. That's negative, which means that that is inverted. Okay, it's going to be upside down. So there we've taken care of our converging lens. Let's look at the diverging lens. The object is 12.5 centimeters in front of that. We still have the 10 centimeter focal length. So in this case, again, 1 over f is equal to 1 over dO plus 1 over di. And again, we can then write this as 1 over di equals 1 over f plus, minus 1 over dO. In this case, f, since this is a diverging lens, f is minus 10.0 centimeters, and dO is 12.5 centimeters. Okay, so putting those values in to this equation, we get 1 over di is equal to 1 over negative 10.0 centimeters minus 1 over 12.5 centimeters. And again, if we go to our calculator to do that, we have minus 10, 1 over that, minus 12 point, oops, missed the 12.5, next to the minus 1, get our answer, and that's 1 over the image distance. If we take 1 over that, we get minus 5.56. Minus 5.56 centimeters for our object distance. That means that the object is on that the image is on the left side of the lens. Okay, it's on the same side as the object, but it's going to be smaller. All right, and now we can again use our magnification. It's minus di over do, which would be minus negative 5.56 divided by 12.5 centimeters. All right, and I am going to use my calculator for that one, so I'll bring that up again. And I had minus 5.56 divided by 12.5 gives us minus 0.445. Okay, so again, this one would be a little bit less than half the size. The object would be a little bit less than half the size of the object. Okay, here we are back at our PowerPoint again, and we'll continue on. I wanted to just take a look at the ray diagrams that they had done for this problem, and you'll notice that for our converging lens here, you notice that the image is inverted and it's real. It's on the opposite side of the lens as the object, and of course it's diminished. We got 0.5. That should be half the height of that one. You can't tell that in the diagram here, but I believe it is. On this one, for the diverging lens, we found that the image was virtual and it was upright, not inverted. And again, this shows that, and so our calculations are probably correct. Okay. All right, let's move on to eyeglasses. The front of the eye, the cornea, acts a little bit like a lens, and then you also have behind that a crystalline lens that refracts the light towards the retina, which is the light-sensitive part of the eye. The lens in the eye is really something that we haven't been able to replicate yet. We can transplant lenses into people's eyes. Some people, when they get if they have cataracts, which is a clouding of the lens of the eye, the lens can be replaced, but it is no longer it no longer functions like the original lens. The original lens, the lens that you have in your eyes, is able to actually change its shape so that it refracts more or less. And so you can focus your eyes on a very close object. You can also focus your eyes on a very distant object. And this is done. You learn how to do this as a very young child, and we do it all the time without really even paying any attention to it. But it is due to the ability of our lens to move and to change its shape. There are two conditions, myopia and hyperopia, short-sightedness and sometimes referred to as farsightedness, that occurs when light is not properly focused on the retina. And you can use converging and diverging lenses to correct those conditions. If you look here, farsighted, in a farsighted person, a nearby object, that object will be focused. The lens is not able to properly correct, and it's focused beyond the retina. The retina is this back part of the eye here. So this is referred to as farsightedness. Usually people that have this condition have very, very acute vision for distant objects, but objects close up, they need some help. And so this can be corrected using a converging lens, which causes the rays of light to go together, to converge a little bit before they enter the eye, and then the lens further brings those to focus on the retina. So a converging lens helps farsightedness. Nearsightedness, a nearsighted person is not able to properly focus distant objects. These rays of light that are parallel or nearly parallel get focused at a point in front of the retina. Again, the retina is in the back of the eye, and so what we have to do with this person is to give them a diverging lens that spreads the light rays out before they enter the eye, and then the lens bends it back to fall on the retina. Okay, so both of those conditions can be corrected with lenses, or of course you could use by putting the lens right on the cornea here. You can correct it that way, and that's what a contact lens does. Lenses are often used in combinations also. And what happens is you use the image formed by one lens to serve as the object for a second lens. Compound microscopes do this. They use two converging lenses, and they achieve greater magnification than either of the lenses than is possible with either of the lenses by themselves. Refracting telescopes. Now these are different from reflecting telescopes. Reflecting telescopes use a mirror. Refracting telescopes use two lenses. One of the problems with a lens is that you can only make it so big before it begins to sag under its own weight. And once that lens starts to sag, that changes its shape and it doesn't refract the way it's supposed to. And so refracting telescopes are limited in their size. They can be made somewhere up to about 3 feet or about 1 meter in diameter. And then the lens becomes too heavy, and because you can't support the lens, it starts to sag, and it deteriorates the image formed.
A compound light microscope uses two converging lenses to create a highly magnified image. The two lenses are called the objective lens and eyepiece lens. The lens closest to the object is called the objective lens. The object being examined is located at a distance of between 1 and 2 focal lengths from the lens. At this location, the objective lens forms a real image of the object near the eyepiece lens. The image is located within the focal length of the eyepiece lens. Because the image is within the focal length of the eyepiece lens produces an enlarged virtual image of the first image. The two lenses produce a greatly magnified virtual image of the object. Magnifications of 1,000 times are common in compound light microscopes.
Okay, and then a refracting telescope. Here's the way they work.
The arrangement of lenses in a refracting telescope allows distant things to be magnified. The lens of a refracting telescope furthest from the eye is called the objective. The object being examined is at an effectively infinite distance. The focal point of the objective is closer to the eyepiece than the focal point of the eyepiece. This causes a real image to appear very close to where the eyepiece is. The magnification power of the eyepiece causes a much larger virtual image to form. This allows distant objects to be observed in detail.
Okay, and again, remember she said because we're looking at, with a telescope, you're looking at objects that are so distant, the rays of light from them are coming in effect parallel to each other, and they will then form an image real close to the focus of this lens to there, and then that is placed such that the eyepiece lens magnifies that image. And I think, yes, that does it for us for today.